There are several common types of refrigeration systems in use today, and they all accomplish the same basic task. They remove heat from an area or substance and keep it cool. In this part, we'll look at how a typical vapor compression refrigeration system works. We'll use some approximate temperatures and pressures as we trace the flow of refrigerant through the system. Here is a simplified illustration of a typical vapor compression system. The main components are an evaporator, a compressor, a condenser, a receiver, and an expansion valve. When the expansion valve is open, it allows the liquid refrigerant to expand into an area of low pressure. The refrigerant that leaves the valve is in the form of a liquid vapor mixture. This expansion causes the pressure and temperature of the refrigerant to drop. In this system, the refrigerant that leaves the expansion valve is at a temperature of about 5 degrees Fahrenheit and a pressure of about 25 psia. Next, the refrigerant enters the evaporator, where it absorbs heat from the evaporator's surroundings and changes completely to a vapor. As the refrigerant absorbs heat, it cools the evaporator's surroundings. Because of the temperature difference, heat continues to transfer to the refrigerant. As a result, the temperature and pressure of the refrigerant increase slightly. From the evaporator, the refrigerant is drawn into a reciprocating compressor. The compressor increases the temperature as well as the pressure of the refrigerant. The refrigerant is forced out of the compressor at about 125 degrees Fahrenheit and 180 psia and sends it on to the condenser. The condenser is a shell and tube heat exchanger that uses water flowing through the tubes as a cooling medium. The water removes heat from the refrigerant, and the refrigerant becomes a liquid again. The refrigerant flows next into the receiver. Here the refrigerant is at a temperature of about 100 degrees Fahrenheit and a pressure of about 130 psia. From the receiver, the refrigerant flows back to the expansion valve and the cycle continues. Absorption refrigeration systems use chemicals called absorbents to control the pressure and temperature inside the system. A common application of a typical absorption refrigeration system is to cool water. The cooled or chilled water is then pumped to various components where it absorbs heat. We can look at an illustration of an absorption refrigeration system to see how it works. The example system consists of 4 main sections: an evaporator, an absorber, a generator, and a condenser. To see how this system works, let's start with the evaporator section. The water to be cooled or chilled water flows through tubes in the evaporator section. Refrigerant, which is also water, is pumped from the bottom of the evaporator and sprayed onto the tubes. As the heat transfers to the refrigerant, the chilled water cools and some of the refrigerant vaporizes. Any refrigerant that does not vaporize collects at the bottom of the evaporator. The temperature of the chilled water is typically too low to vaporize the refrigerant at atmospheric pressure. This system operates at a very low pressure to allow the refrigerant to vaporize at low temperatures. In our example, the pressure is around 0.15 psia. At this pressure, the refrigerant will vaporize at 45 degrees Fahrenheit. The low pressure that's needed is achieved by using a chemical absorbent such as lithium bromide. The refrigerant vapor from the evaporator flows into the absorber section, where a relatively hot lithium bromide solution is sprayed into the vapor. The lithium bromide absorbs the vapor, and a mixture of absorbent and refrigerant is formed. When the lithium bromide absorbs the vapor, the volume of the vapor is greatly reduced, which causes the low pressure. The lithium bromide and the refrigerant will be reused in the system, but to do this, they must be separated. The separation takes place in the generator section, which means that the mixture, called weak absorbent, must be pumped to the generator. However, the weak absorbent is hot enough to boil inside a pump, so it must be cooled first. The cooling takes place in the absorber. Cooling water passes through tubes inside the absorber and cools the weak absorbent flowing around the tubes. From the absorber, the cooled weak absorbent is pumped into the generator section. In the generator, the weak absorbent is heated by steam passing through tubes. When the weak absorbent is heated, the refrigerant boils off, leaving the lithium bromide behind. This lithium bromide is called strong absorbent, since it has a strong ability to absorb refrigerant. The refrigerant that boils off in the generator is sent to the condenser. We'll see what happens there in a minute. The strong absorbent is sent back to the absorber. On its way, it passes through a shell and tube heat exchanger. Weak absorbent on its way to the generator also passes through this heat exchanger. In this heat exchanger, the strong absorbent gives up some of its heat to the weak absorbent. Cooling the strong absorbent increases its ability to absorb the refrigerant vapor when it's sent to the absorber. This helps to maintain the low pressure in the unit. Heating the weak absorbent increases its temperature, so less steam is needed in the generator to separate the refrigerant from the absorbent. This makes the system more efficient. Meanwhile, in the condenser section, the refrigerant vapor flows around tubes and is cooled by cooling water passing through the tubes. As the refrigerant gives up heat, it condenses and forms a liquid that collects in the bottom of the condenser. The liquid refrigerant in the bottom of the condenser drains into the evaporator. In the evaporator, the refrigerant from the condenser mixes with the refrigerant that is already there, and the cycle begins again. In this topic, we looked at the operation of a typical vapor compression refrigeration system and at the operation of a typical absorption refrigeration system. Take a moment to try some practice questions on this material. Next, the refrigerant enters the evaporator, where it absorbs heat from the evaporator's surroundings and changes completely to a vapor. As the refrigerant absorbs heat, it cools the evaporator's surroundings. The low pressure in the system is achieved by using a chemical absorbent such as lithium bromide. The refrigerant vapor from the evaporator flows into the absorber section, where a relatively hot lithium bromide solution is sprayed into the vapor. The lithium bromide absorbs the vapor, and a mixture of absorbent and refrigerant is formed. When the lithium bromide absorbs the vapor, the volume of the vapor is greatly reduced, which causes the low pressure. A refrigeration system lowers the temperature of a substance or an area. The controls used with a particular system depend on the system and how the system is used. To operate properly, a refrigeration system must control refrigerant pressure and flow. In a system that has a reciprocating compressor, the flow of refrigerant is produced by the pressure exerted on the refrigerant in the compressor. Some types of refrigeration systems maintain the desired amount of cooling by cycling the compressor on and off. This controls the amount of refrigerant that flows to the evaporator. In many systems, refrigerant flow, and therefore the amount of cooling, is controlled by an expansion valve. The position of the expansion valve is controlled by the temperature of the substance being cooled. Some control systems use a thermostat located in the area being cooled to position the expansion valve. Other systems may use a thermal bulb or a thermocouple. We'll use an expansion valve and a thermal bulb to see one way to control the amount of cooling that a refrigeration system provides. This illustration shows the expansion valve, the thermal bulb, and connecting tubing. A metal bellows inside the expansion valve is connected to tubing that leads to the thermal bulb. The thermal bulb, tubing, and bellows contain a fluid that expands when it's heated and contracts when it's cooled. The thermal bulb is mounted on the refrigerant line between the evaporator and the compressor. It senses the temperature of the refrigerant leaving the evaporator. The temperature of the refrigerant is proportional to the temperature of the substance being cooled. For example, if the temperature of the substance increases, the refrigerant's temperature increases as well. So if the temperature of the substance being cooled is above its desired value, the temperature of the refrigerant will also be higher. Heat in the refrigerant will transfer to the thermal bulb, and the fluid in the bulb will expand. This expansion forces fluid into the metal bellows. What do you think happens to the metal bellows? The fluid causes the bellows to expand and open the valve more. This allows more refrigerant to flow through the expansion valve. In the evaporator, the additional refrigerant removes more heat from the substance and its temperature decreases. If the temperature of the substance being cooled goes below the desired value, the temperature of the refrigerant leaving the evaporator will decrease. In this case, the refrigerant absorbs heat from the fluid in the thermal bulb, and the fluid contracts. This causes the expansion valve to close slightly and reduce the flow of refrigerant to the evaporator. Now that we've seen how flow is controlled, let's see how a system maintains pressure. As you may recall, the pressure exerted on the refrigerant in the compressor creates the flow through the system. Let's look at a refrigeration system that uses pressure switches to help maintain the proper pressures in the system. This system has a low-pressure cutout switch located on the compressor suction. It also has a high-pressure cutout switch on the compressor discharge. When the system is operating and the temperature of the substance being cooled drops, the temperature and pressure of the refrigerant entering the compressor will also be lower. If they get too low, some of the refrigerant will not vaporize and will remain as a liquid. If liquid refrigerant is allowed to enter the compressor could be damaged. So when the pressure of the refrigerant decreases below the set point for the low-pressure cutout switch, the switch shuts off the compressor. Refrigerant continues to flow through the evaporator and absorb heat. More refrigerant vaporizes and the refrigerant pressure increases. When the pressure rises above the set point of the low-pressure cutout switch, the compressor will automatically restart. The high-pressure cutout switch prevents the compressor from overpressurizing the system. In systems with centrifugal compressors, the compressor runs continuously, and there may be additional components to maintain the desired values. For example, in this system, a bypass line routes some of the refrigerant around part of the condenser, the receiver, and the expansion valve. When this is done, the refrigerant that flows into the evaporator is warmer. The flow of refrigerant through the bypass line is controlled by a control valve to maintain the temperature around the evaporator. If the temperature around the evaporator gets too low, the temperature of the refrigerant flowing to the compressor will drop.